So we've just finished a design review with Echion. Yeah, the design review was an important milestone in the project as we transition from systems being designed to systems being physically built. A couple of key items, unsurprisingly, that came up that need to be specifically addressed, and the team's going to talk about them now.
Today we did the design review. It's the one and only design review for this project for the purpose of keeping it fast and smooth as possible. They are a necessary evil to do a design review. Without such thing, you cannot pull everyone together and ensure that you're on the same page. You can't ensure that you have interfaces between people and components that match. So they're a very important part of any project.
So we just finished our design review with Echion. So we had Nathan and Ben in the room, and just a pretty standard design review, check off everything, see how we're going with the budget, lead times on things, making sure we've ordered everything we need to. I got to speak mostly about the battery modules, the battery pack itself, and how that's going to interface with the rest of the car. So that being the combiner box and the cooling system. We have done some wooden mock-ups. So these are just some MDF battery cells. So this is the rough outer dimensions of the batteries themselves. Two packs here next to each other. We're calling them sub-packs. Together they make one big pack. Out the back we will have coolant fittings. So coolant will stay down this side. It will run to the front of the battery and then back. We'll do that 4 times on the modules. Again, 2 more here. We will join that and we'll go off to the rest of the cooling system. We will have our pressure burst vent at the back as well. When you use these type of cells, if they get hot and they enter thermal runaway, the first thing you try and do to prevent that from being absolutely catastrophic is to vent all of the pressure. So they will be at the back here. We'll have some internal manifolding sort of in this section here, just before the actual cells start. And this will split it to the different cooling plates inside. So if we walk around to the front now, or sort of the side, just before you get to the cab. Not a great spot to show it maybe, but we'll have our combiner box at the front. So the combiner box, we've got a bit of a space claim here. Yeah, so 2 90 degrees HV cables. So they will run out like this, out the front of the pack, and they will join to the combiner box on the underside. So we don't really have any room for connectors on the front. At the cab side, again, we don't really have any room for connectors on here. So everything's going to have to be bottom addressable. That includes the maintenance service disconnect. So on a system like this, you want a single place for you to open the HV circuit, and that will be on the combiner box underneath. Each battery will also have a MSD, or maintenance service disconnect, and that will, once you open it up, make the 2 points of HV dead. So if I just grab one from over here, this is an example of a MSD. When it is closed, then these two are joined, and it means you've got HV on the outside of the pack. It's a couple-step process on opening it. Once you have this, and that will be exposed on the front of the battery, it is now no longer connected, and you cannot possibly get HV out the front. The contactors will also be open, and this is your sort of final line of defense. That means that when this is pulled, we can move the batteries, disconnect them, join them up to the combiner box, lift them into the car, and do whatever we need. Again, the front of the batteries will have a comms connector, so CAN bus in, out to talk to the rest of the car, and we'll get all our data in and out of the batteries. And yeah, that's probably all there is to say.
We just finished our design review meeting with Echion, and the number of good points that were brought up on the current software design. I think overall they were pretty happy with the way the software side of the control system is progressing and our current design, but there's definitely a few issues to solve. They wanted to know a bit more about how the driver is going to operate our control system and interact with the hybrid system. And so I presented some pretty pictures of a user interface design, like a screen, some buttons and some gauges showing different information about the battery and motor inverter. Recently, we've kind of got our first implementation of this system. Although it's very simple, this is something like what the gauges are going to look like. This is definitely going to change a lot, but the idea is we're showing negative 100 to positive 100% motor torque. So as you accelerate, this gauge will go positive. As you're accelerating, as you're regen or braking, it will go negative. And some other gauges for battery SOC, like state of charge and battery temperature and vehicle speed. I still got to add some buttons, but we got most of the functionality there now. This is talking over a CAN bus to our ECU, so we can update these values from the ECU and the rest of the control system.
We recently had our design meeting for the Land Cruiser project, and during that we discussed the battery management system architecture and some concerns about the cell balancing capabilities of the battery management system. And we have gone and done a bit of work on that and have finalised the printed circuit board design for the battery management system. We have increased the cell balancing current to help keep everything in check and things running nicely. Cell balancing is a crucial area of the battery management system because each cell in the battery, which there are 256 of, has very slight manufacturing differences. So some have a slightly bigger or smaller capacity, some have slightly different internal resistances, and as the battery is used, current goes through it, that can lead to a mismatch in the voltages in the batteries. And so the battery management system is responsible for trying to bring all those individual cells back to the same voltage so that you don't hit any protection points unnecessarily. If the battery does go out of balance, you'll have your highest cell voltage limiting at the top end of charge and your lowest cell voltage limiting at the bottom end of charge, which reduces your overall capacity of the battery. So I'll show you where we've ended up with our module and the battery management system and how it all comes together. So previously, I think I had shown some of the early revisions or the prototype boards that we were using for the battery management system. We've since progressed onto the final designs, and you'll see here we have our analog front end, which monitors a group of 32 cells, and that is mounted to the side of each module. There's 8 modules, each with 32 cells in them, and the analog front end connects to the cell module through a flex rigid PCB where the cells are attached to. We have put extra focus into the thermal capacities of the analog front end to ensure that we can really push that balancing current up. The cell balance resistors have also been altered so that we can reduce the balancing circuit resistance, which allows us to get up to the design requirement of 240 milliamps. We're utilising a 4-ounce copper for the flex rigid PCB to give us the best heat dissipation, and a 2-ounce copper for the analog front end on the external layers to allow all of that current to flow around without overheating or hitting thermal limitations. We're using 8 thermistors for the top side and another 8 for the bottom side so that we can carefully monitor the temperatures that are hit during cell balancing and ensure that we're not at risk of doing any damage to any sensitive components. Overall, we have pretty much finished product that will be going up for manufacture, and within a week or 2 we should have our final versions here.
review, we have an issue with the mounting of the motor, where the motor has to be placed to fit in with the rest of the system. We are going to have to delete one of the existing cross members out of the chassis, which is this one. We've discussed in the meeting the effects that's going to have on chassis stiffness. The idea is to remove this cross member and replace it with a similar cross member that allows us to mount the motor. So yeah, there'll be a fair amount of torque being transmitted into that from the motor, and then it's obviously got to hold the chassis rails apart and do all the things that this existing cross member does. So part of the ADR compliance will be proving that our replacement cross member is at least equivalent, if not better, than what we've removed. The way we're doing that is with simulations on the computer. So we've modelled up what's there. We've run some analysis on that. We know how strong, how stiff that is, and what we're replacing it with is significantly stronger. And it's likely to be over-engineered, what we're replacing it with, but the downside of using the thick material, I'll say, is weight. The upside is we're not going to have to worry about it. And with the type of vehicle it is, it's not a race car. We're not worried about every last kilo. The easiest, most time-effective solution is to over-engineer it slightly and then not have to worry about it down the road.
For those that have been following the series so far, it's about introducing the team. But now that we've done the design review and we can make things happen, it'll start getting much more interesting. You'll see things coming together, you'll see the vehicle taking shape, and ultimately we'll have a completed project and be able to show you guys how it performs on the road and all the lovely things that we want to do with this car.
If you find this interesting and you want to follow this journey, then please like and subscribe. There will be plenty more.